So good morning all. So last class we were discussing on the radial and hoop stresses in and stress concentration around a large plate which is having a small hole in it. Okay, with that we have finished our third module, that means the polar coordinate system. Now we are going to take another topic. Academically it will be module 4 of the course Advanced Mechanics of Solids, ME 202 from KTU. Okay, and that is strain energy. So what do you mean by strain energy? So when a load is applied on a body, the body is deformed. That means if you apply a load on this body, if you have a body, you are applying a load, you are pressing it, the object can be deformed. Okay, now this deformation is associated with a work. Okay, this is deformed due to some work that has done from my fingers. Okay, so a work is done by this application of load. The work is absorbed by a form by the body in form of energy. So if I am pressing this work which I am doing, it will be absorbed by this object in the form of some energy. Okay, this form of energy is called as strain energy. That means the energy in which the object is strained is called as strain energy, which is nothing but it's just the work done by the application of force. Okay, so when the load is removed, body regains its original shape by using this stored energy. So here we'll recollect the stress strain diagram of mild steel, in which you have an linear curve up to the point B. Okay, from there you know what the process is happening. So we are dealing only with elastic limit. Up to elastic limit, we'll be dealing only up to this elastic limit. Okay, so strain energy is simply the energy stored in the curve with the strain curve, with the strain line. That means the area of this triangle. By definition, when a body is strained from initial unstrained condition to final strain condition, the amount of work done on it is the total strain energy. Okay, if I am pulling this object and this is having a small strain, for that this is the initial position, and if suppose this is a plastic, so and I am applying load so that this is extending. So from this position up to this position, what is the work I have done? This will be stored in the form of an energy, and this is called as simply strain energy. Okay, you might have studied all these things in mechanics of solids. So so I have discussed earlier, from this figure strain energy can be found out by just finding the area of this triangle, that means the shaded portion. Once this body is unloaded, only a part of this energy is recovered. So if I release the force on this object, this retains to its original shape, right, for an elastic member. But at that time the energy is restored. The energy restored is not what energy retained. Okay, only a part of the energy will be restored. Okay, and this is called as elastic strain energy. Now see, for a perfectly elastic material and for non-linear elastic material, the graphs will be like this. One is straight and the other one is somewhat you can draw like this. Okay, like this you can draw. Okay, so what happens is that simply the concept is that strain energy is the energy stored, that means it is this triangle. Strain energy is the area of this triangle, that means area under elastic curve and the deformation curve. Whereas restored energy, that means if you release the load, it will be having an energy U star, that is called as complementary energy, which is found by the area under the curve or area between the curve, elastic curve and load line. Okay, so that has been given here. Area enclosed by curve and deformation line is called strain energy, which is denoted by U, and area enclosed by curve and deformation load line is complementary strain energy, which is given by U star. For linear elastic material, U is equal to U star. That you can see. If this is linear, then this triangle and this triangle will be having same area. Whereas here, this strain energy is greater than this complementary strain energy. Okay. So how will you find out the strain energy of this? In two ways you can find it. Just find the area of this triangle, you will get the answer. Or else, what is strain energy? It's the work done, right? Work done is force into distance. So average force, if I am pulling an object with a force P having length L and it is deforming L, and it is having an elongation of dl, that means the force applied here is from 0 to P. So you need to take out the average force, 0 plus P by 2, which is equal to P by 2. Distance will be, that means elongation is dl, then P by 2 into dl is the total strain energy. Okay, otherwise you can also find out the area of this triangle in load deformation curve. That means this is dl and this is P, and this length is P and this is dl, half into base into height, that is P half into P into dl. Same answer you will get, half into P into dl. Okay, where P is the load applied and dl is elongation or deformation, which is given by PL by AE. Okay, now next term is strain energy density, or otherwise it is called as resilience. It is nothing but the strain energy per unit volume. Okay, so strain energy per unit volume is called strain energy density or resilience. So you know U is equal to 1 by 2 P into dl by V. V can be written as area into length. Okay, P by A into dl by L. P by A is stress is force by area, and strain is elongation, change in length by original length. You will get 1 by 2 into stress into strain. So strain energy density is given by 1 by 2 sigma epsilon. Okay, now you can again from Hooke's law we know that E is equal to sigma by epsilon. So epsilon is sigma into sigma by E. You substitute this one, instead of epsilon you will substitute this value, that means you will get U by V. The strain energy density is given by sigma square by 2E, which is a very important equation. Okay, so there is one more term called proof resilience, which is given by the resilience corresponding to stress at elastic limit is called proof resilience. That means the elastic limit at, say, at this point B, what will the maximum stress? So that will be sigma E square by 2E, where sigma is the stress at elastic limit. Okay, now you have to find out the general expression for strain energy. That means you are having an object which is having dx, dy and dz dimensions along its x, y and z directions. So what will be the total strain energy of this object? So this can be found out by Total strain energy is nothing but work done, which is force into distance by 2. We already know that. So energy due to sigma x, consider only sigma x is having a stress along this direction. Okay, so energy due to that will be ux is equal to half into dy into dz. That means area. That means sigma x is acting along this area, dy into dz. Okay, so area into sigma x, that is nothing but force. Okay, force is sigma into a. That means you got this force, and distance is, what is the elongation? That means strain into, see, strain is change in length by original length, so dl will be epsilon into length. Here the length is dx. Okay, so ux can be given as 1 by 2 into sigma x epsilon x dx dy dz. Similarly, if you need to find out the whole structure, if this structure is having all sorts of stress like sigma x, sigma y, sigma z, and also shear components, if all the 6 components are available, then the equation becomes 1 by 2 into integral, triple integral, volume integration of this sigma x epsilon x plus then sigma y epsilon y plus sigma z epsilon z plus shear components, the whole into dx dy dz. So this is the strain energy due to all the 6 components of forces. Okay, so when we consider a body like a bar having length in x direction, and if only considering the x direction, which is having axial stress as well as shear stress, then it becomes 1 by 2 into sigma x epsilon x plus tau xy gamma xy. Okay, dx dy dz. Instead of sigma x epsilon x, substitute this value sigma x square by e, that we have already found out here. Okay, sigma by e, instead of this one you will this. Similarly, epsilon, see, this becomes g is equal to, what is shear modulus? Shear modulus g is equal to shear stress by shear strain. Okay, from that you will get this equation. So this is the common term or the general expression for strain energy. Okay, so hope you got all these things. We'll continue in the next lecture. Thank you.